as engineers, as a group of technologists, we've had to retrain massively over the years, and long may it continue. So I also editor of the Broadcast Bridge, and if you haven't subscribed to the Broadcast Bridge, please do. It's free to do so. It's a technical publication. Our motivation is to share knowledge and help people understand what's going on from a technology point of view within the industry. And a lot of the articles we write are vendor neutral, so you get some good hardcore technology, which is written by myself and several of my colleagues, some of whom are in this room. I'm a committee member of the RTS and Thames Valley Technology Centre, an associate tutor in broadcast engineering at the University of Surrey, where I was earlier today. And I'm also a PhD student at the University of Surrey, where my current research is IP timing anomaly detection using machine learning. So I've got one foot in IP, another foot in machine learning, so get the best of both worlds. And what I'm going to talk about today is sort of the subject of my research, so that we can get a feel for what's going on in IP networks and how we can use machine learning to help us leverage the systems more efficiently. So, the objectives for the talk are to give an overview of network congestion and its relevance to broadcasters, explanation of why congestion control is important for ground to cloud, so I'm predominantly going to be focused on ground to cloud today, and a discussion of how ML combined with SDNs can help reduce latency in vendor agnostic ground to cloud solutions. So vendor agnostic is key for me because that's where a lot of my research is. I know you could go to some vendors and they may provide an entire solution for you, but what I'm trying to talk about here is systems where you don't have to rely on vendor lock-in. So if you understand more of the system and how it works, the less risk you then have to rely on vendor locking. You may want to do vendor locking. I'm not saying you should or shouldn't. I'm just putting forward ideas so that you have the choice. So again, beautifully following on from what Paul and David were saying, we need to think differently. The cloud isn't, if we just take our existing workflows, push them into the cloud, we've completely and utterly failed. It won't work anyway. So broadcast engineers need to think asynchronously. We've always worked with sampled synchronous systems. That's what television is. There are no moving pictures in television, just a series of still images played back very quickly to give the illusion of motion. And so all these images have to be synchronized, all our audio frames have to be synchronized. But as we move into the cloud and IP generally, we have to start thinking asynchronously because that's how IT works. IT engineers and developers need to think synchronously, not because we're going to do anything synchronously going forward, but because they need to think what the broadcast engineers are thinking, so they can have sensible conversations. And when we all get that together, it all becomes quite clear of what we're trying to achieve. And finally, failure is a reality of life. I mean, throughout my career working in television, I've worked with some big broadcasters, we've always had these A/B failover systems, and they always work when you're testing them. Sunday mornings, always guaranteed, switch the power off, UPS comes on, generator comes on, and it works for half an hour and everyone's happy. Except on a Monday morning when you're about to put your first ad break out. And it's on for 45 minutes and somebody forgot to check that because your generator is on a canal, your TV station is by the side of a canal, the generator gets very warm, which keeps the local rat population very warm, and they like the exhaust areas, and they build a nest around the exhaust port, and then after 35 minutes, it sets on fire. So failure is something we can't predict by definition. So when we move to the cloud, we have to accept failure. It's a consequence of life. Nothing works perfectly 100% of the time. We must think in terms of probabilities. This is just basic physics. Okay? We can't guarantee anything. We can only say with a certain amount of probability an event will probably happen. So I think it's worth recapping that IP is such a big subject. We use it in different ways throughout our broadcast environment. So this is where we've come from. This is sort of where we really are at the moment in terms of RF transmission. This is our bread and butter. This is going. At some point, all our transmitters will be switched off, and we're going to be going over the cloud. and delivering into people's homes through ISPs and through cable, sort of internet cables and such like. In this context, in the OTT context, we use TCP IP. Within our studios, and there are cables there, within our studios, we mainly use UDP and multicast. Here we generally use unicast. Now there is talk about doing multicast in the cloud, which is an entirely different subject, and we'll come on to another talk. But here, this is the area I'm focusing on for this talk, and this is the ground to cloud, where we take our studio feeds and we pump them into the cloud and we receive from the cloud. Two main methods of using this is TCP IP or ARQ IP. We'll come on to ARQ IP in a little while. I'm just going to focus on TCP IP at the moment because the general consensus is never use TCP IP. And to a certain extent, you're right, but I just want to recap on why that's a challenge. Because one of the benefits I've had of studying for my PhD is that I have the opportunity to understand stuff which people don't always have the time to sort of learn about. So I can really dig into the weeds of this. And what's more, it's positively encouraged. So network and sources of latency. IPs are inherently lossy. That's something broadcast engineers are having to come to terms with. We've always worked with, prior to SDI there was PAL, but with our SDI networks, AES, even analog networks, we've always assumed they are lossless. They're not. It's just that the losses we had were almost unviewable. I mean, with SDI, there's a CRC there for a reason, because occasionally packets get corrupted or data gets corrupted. It's just so minimal that we never noticed it. And we were also working with circuit switch networks. So we had the benefit of guaranteed bandwidth. We have a guarantee of latency. In the IP world, even with your ST2110 non-blocking switch super duper system that you've got in your TV station, you're going to lose packets. It's just they're so few and far between, you're not going to notice them, hopefully. TCP helps fix that in the IT world because it guarantees delivery of IP packets, but at the cost of latency. And we'll come on to that in a sec. Because TCP uses the retransmission clock to determine lost packets. So in other words, what we're doing here is we're sending a packet into our network and we start a clock and it gets received by the receiver says that's great and sends an ACK back. And then that whole thing keeps going. And so a consequence of TCP is that when you send packets into a network, it self-regulates using this data and ACK system to be able to make the most of the bandwidth available. Because the other thing that's different for broadcasters, we have to remember that we've always had the benefit of knowing what the bandwidth or the data rate of our circuits are. So 270 megabits gives us 270 megabits. 1.485 gigabits gives us 1.485 gigabits. 10 megabits on an IP link, who knows? Because you don't know what you're connected to. That's the whole point of networks, is they are flexible. But flexibility comes at a cost. So when we send our packet into our receiver here, and this could be a microphone sending a packet into a receiver, a sound console. The sound console sends the data back and says, yes, I'm okay, I've received that packet, now send me another one. So it self-regulates the available bandwidth. If a packet gets lost here, here, or here, or this operating system gets busy and can't return quickly enough, this RTO clock keeps ticking. And when it times out, then the TCP generator says, it hasn't been received. So it will resend the packet. What is the RTO clock set to? It depends. If you're using Linux, it could be seconds, or it could be milliseconds. It all depends on how the system's been set up and configured. So all of a sudden, you have a system which, yes, it self-regulates, but if data packets do get lost, you don't know where, and the only solution, the only remedy is to resend the packet. So if the ACK gets lost here, and the data has been received, the sender will still resend that packet. So it's relatively inefficient. But, and this is what I mean when I say that it guarantees delivery, but at the cost of latency. packet loss due to congestion leads to latency. That's just worth bearing in mind for a short time, because you might be thinking, people who know about these things, that's easy because I can just use ARQ, an ARQ-based system, and this problem goes away. Almost. So this is some of the TCP flows I've been playing with within the university. There are standard data sets, a cable. There are several standard data sets that we can use within academia, and these are all publicly available so that academics can compare their notes and compare their results. This is something called a CAIDA dataset, which you can download free of charge if you like. They go back a number of years, and they're basically PCAP stream grabs from Wireshark of backbone networks or ISPs, whichever one you download. And what I did as the first part of my research was start building the TCP streams and graphically represent them to see what's going on. So here we have a short bursty flow, even though it may look probably long, because the time scale here is hundreds of milliseconds. So this one and this one have an average data rate of a few kilobits per second, but you can see there are massive peaks here and here, where they peak up to 100 megabits per second, only for a very short space of time. So the average is very low, but you get this instantaneous peaks, which is fine, because that's how it's supposed to work. Now, in our broadcast engineering hats on, we think, oh, get rid of these and average it out, because that's what we do in SDI, but not in IT. Now, some of these longer flows are more descriptive of either a video download or possibly an FTP download, or somebody have an operating system download. When you have a look at these data sets, you've no idea what these things are doing, other than you just get the IP addresses. So you just know there is a long data flow going on here. Now, in these networks, what we've found, and this is sort of research over a number of years, I mean, this goes back 10, 20 years, is that 80% of the traffic is due to a small number of steady elephant flows. So new terminology, we use the word elephant flows, and remaining traffic is due to high number of bursty mice flows. So within our TCP network, we have things called elephant flows and mice flows. Now, that's, again, the TCP guarantees packet delivery through the data ACK flow control. So that's, send a packet of data, the receiver then sends an ACK, then the sender sends a new packet of data, and this is going backwards and forwards. We need something called congestion control to avoid congestion collapse. I'm going to come on to that again in a few minutes, but this is where ARQ possibly breaks down. So what is asynchronous packet delivery like? Now, in a broadcasting environment, if we were to have an SDI router, we would have, 256 inputs, 256 outputs. You could guarantee that you could route any one of those inputs to any one of those outputs. When we move into asynchronous packet delivery, so this is just IP packets, you have servers, microphones, sound consoles, vision switches, production desks, whatever you want to have here, have these 10 gigabit per second links, for example. They could be something else. And the switch is connected via a 40 gigabit per second link here on this example. So if all of these devices play nicely and average less than 40 gigabits per second, that's fine. But statistically, they won't all be sending 40 gigabits per second, like here, because we're going to get these big transient peaks. We'll come on to that again in a sec. So this is just really demonstrating that the potential here is for 10 times 10, which is 100 gigabits per second, to go into a 40 gigabits per second link, which will result in packet loss. Because, well, we'll come to why in a sec, but that is the worst possible case scenario. Now, in the IT world, we assume that won't happen, because if you've got 10 computer servers, all with 10 gigabit links, the probability of all of them sending 10 gigabits per second simultaneously is very, very low. If you're in a broadcast television environment and you've given a camera a 10 gigabit per second link, the probability of it sending 10 gigabits per second is very, very high. So our options are, we use non-blocking switches. non-blocking switches seem to be the answer to all of our problems, because we can put 10 gigabit per second links from 10 cameras into our switch, and assuming this was 100 gigabit per second, then we would have our buffer, and we would only sort of slowly fill up our buffer, and we would never overflow it. That's the essence of a non-blocking switch. Now, where do we find non-blocking switches? Normally within the studio environment. So when people build ST2110 systems, the first thing they buy is a PTP clock. The second thing they buy is a non-blocking switch. So this guarantees our data throughput, but the non-blocking switch is one, incredibly expensive, and two, forms part of a managed network. Now remember at the beginning in my cloud bit there, I said we're going from ground to cloud. I'm using cloud in the context here where it's a public cloud. So once it leaves the studio, we have no control over the hardware. We know the hardware is fundamentally there, we can configure it, we can see what it does, but we fundamentally don't have the level of control over the hardware we would have in our own data center. Sorry, broadcast infrastructure. So you can see another thing what's happening here is we're getting these elephant flows. So the elephant flows are these long flows here, and you can see they're quite cyclic, which is typical of a long-term elephant flow. And the elephant flow is going to fill up generally the buffer to a certain level and then leave space for everything else after it. So that quite often within the switch there'll be an algorithm which says, well, keep the buffer filled to X% unless there's space for it to be completely empty, so that then you can have fair access for all of the devices connected to the switch. Because this is just one device. There could be 100 devices connected to it. There could be 100 buffers. So one of the fundamental rules about networks and the internet in general is the fair use policy. Everybody has fair access to everything. Now the challenges happen with blocking switches, and I'm using the blocking switch name not because they actively block or do something bad, it's just to differentiate them from non-blocking switches. So the blocking switch really describes the kind of the switch within a data center that you have no control over. So you have to assume that your egress port is a contended link, and your elephant flows are filling up your buffers here, but when you get a high burst of mice flow, then the potential is for the buffer to overflow and these packets are dropped. Now you think that's really bad because broadcasters don't lose data. You know, it's built into our DNA. But this is how TCP is designed to work. Because what happens here, if these packets are dropped, from the sender's perspective, they just resend the data. So no problem, which is fine if you're accessing a website and you have to wait, I don't know, 15 milliseconds instead of 5 to access your data, to get your event click through. But if you're in a streaming media facility where you're trying to send the stream video from the ground to the cloud, and some of this, what we could refer to as microburst data, these TCP flows, represent things like keys, security keys, or remote control systems, or just general ancillary data, this will get delayed. So all of a sudden, we have this system where we have these elephant flows and these mice flows interacting negatively. Now these elephant flows are not necessarily the TCP, these can be UDP. So with ARQ, automatic repeat request systems is just data rack. It's TCP. I've got a slide on this in a sec, but it's TCP. It's basically TCP without something called congestion control, but we'll come on to that in a sec. So another point here is that the latency is proportional to the size of the buffer. So, because you could argue, well, why not just increase the size of the buffer? Which you could, but if you increase the size of the buffer, you're going to increase the size of your latency. Broadcasters don't like latency. So, drop packets result in TCP retransmission timeout, which causes latency. Again, it doesn't matter if you're sending UDP, because within a ground to cloud environment, you're not just going to be doing fire and forget. you're going to want some sort of ACK to make sure that your video has got to its destination within, to the server within the cloud, the public cloud. So the solution I'm proposing here is that we need to route EFs, elephant flows, and mice flows separately to avoid link congestion contended networks and avoid drop packets. I'll show you what I mean by that in a sec. So this is an SDN with a controller and switches. Has anybody ever seen this topology before? In the broadcast environment, broadcast engineers, you must have seen this. What do we call this? An SDI router. Okay? Broadcast engineers have been doing this since the late 80s. All right? Because we have switches, which is our fabric, where we have 256 in, 256 out. We have a controller, which is, well, I'm going to use the word Probel panel because that's the one I used to use. So we have our Probel panel, and that whole system can be configured and controlled with software externally. So broadcast engineers have been using SDN since the dawn of time. But this is a relatively new concept to the IT world, because in IT we use things like ECMMP to equal cost multipath to do our signal routing. It's just one of the protocols that we use, but it's an automated form of routing. And it's designed purposely to send packets in different directions should a link fail, so it's resilient. But one of the disadvantages is its variable latency, and you never know where a packet's going to be. So this is one of the areas where this is a typical spine leaf topology that you'd see in a IT data center. And it sort of demonstrates how this elephant flow and mice flow separation works. So in a typical data center topology, you've got the core, two core switches because you've got resilience built into the system. You see the gray lines here show the interconnects, top of rack switches, and then you've got your servers at the bottom. So here, what we're seeing is on the left-hand side, we've got our elephant flow and mice flows coming out as two different servers, going into the top of rack switch, then potentially congesting on this link here, because this is like a single point of failure, and then going over to the two different servers, two different top of rack switches, and then down to their respective servers. And with ECMMP, that will probably be the solution, because it doesn't know anything else. With rerouted elephant flows, what we can do is sell the top of rack switch, instead of sending both to core 0, the top switch, core router switch, send it to the router switch 0, the switch 0 and the other switch 1 in the other, the other part of the spine. So this time you've got your mice flow being sent different link to your elephant flow. So this congestion here, or potential for congestion, has gone. So that's a sort of, I won't say a standard way of working in IT, but it's starting to manifest itself. And this EF and MF detection, classification, has got a lot of research has happened in this over the years. And this is, I wouldn't say, it is something which is available in the IT domain. But what I'm proposing here is that we can reduce congestion using dual links. So in our studio network here, we have our video and audio streaming, and that can be TCP or ARQ. Goes into a router, which is then mixed with control information, monitoring, security keys, remote control data, because you'll probably want to send them over the same link. We then put them into our upload router, our streaming computer, split them into EFs and MFs, and then have one ISP link go to one route, another ISP link go to another route, and then we can process in our public cloud. Remember, this is a generic solution, which shows that there's no vendor lock-in. So that's what I'm trying to achieve here, is avoiding vendor lock-in. So how do we go about configuring this router to differentiate between elephant flows and mice flows? I mean, naively, you might assume that it's easy because an elephant flow is temporally long, so therefore anything over n seconds you can say is an elephant flow. But that means you've got to wait for the elephant flow to establish itself. and it may take a certain number of seconds to do so. At which point you may have already got your congestion, and you might be starting getting to all these time-sensitive mice flows, which things like your control, your security keys, your remote control data. If you're racking a camera into the cloud, or it's going somewhere else probably. I don't think there are many cameras in the cloud, but it's only a matter of time, I suppose. If you're trying to control the time-sensitive event in the cloud, and all of a sudden your control information starts getting delayed because it's getting congestion on the network, if there's just a single link, waiting a second for the router to say, oh, well, that's an elephant flow, I'm now going to send it somewhere else so the mice flow will be fine, is too long. So we have to establish the difference between the elephant flow and the mice flow very, very quickly, the least time possible, hundreds of milliseconds or less. And so just using time as a measure is not the most optimum solution. Using data rate as a measure is also not the most optimum solution for the reasons I showed you with the peak responses. So one of the challenges we have with ARQ, I don't particularly want to talk about specific vendors or open source providers who are providing ARQ type systems, but I'm sure you could probably work it out if you wanted to. What I'm seeing is a lot of even open source solutions using a method of sending massive amounts of data into a network and then waiting for the ACK and then sending another massive load of data into the network. Some people call that network flooding. Congestion collapse manifests high data rate but low throughput due to unconstrained retransmits after packet loss. So this was first discovered back in the 1980s when we were still using, or we weren't, but the universities were still using a variation of ARPANET. And two universities, university between two buildings on a campus found, at the time they had a massively high-speed link. I think it was 100 kilobits a second between the two buildings. And they were seeing 100 kilobits a second of data activity, but they were only seeing fractions of a kilobit a second of data getting through to the end user. And that's because they just discovered congestion collapse. And congestion collapse happens when multiple transmitters are all resending data because their RTOs, their resend timeout clocks, have expired, and they get into a lock. So there's a race-off going on, and nobody wins. So you can imagine 10 transmitters all sending data into the network simultaneously when there's really space for only 2 or 3, and none of the data getting through. So all 10 data senders' clocks expire, so they redo it again. And so the whole system just blocks. And so the way the engineers at the time fixed this was to use something called congestion control. And you can see what's happening here. Instead of just flooding the network with data, we have this slow ramp up. And this is a fundamental part of TCP. This is one of the things that makes TCP so special. And incidentally, it relies on losing a packet to be able to regulate how fast it can send data out. But it only loses it at the beginning. So you can see there's a slow ramp up of data, and then it just goes through this oscillation of sending data and backing off the data, resending data, backing off the data to like a 50% level. This is just one example of how a TCP congestion control system works. There are several different versions. You hear of things like Reno and stuff like that, and they're all variations on a theme of how congestion control works. Some of them even have random backoff. So just like in Ethernet, where if you transmit, you have multiple senders transmitting, they will randomly back off so you don't get the congestion. This is what happens when you use ARQ. You just fill the network, or potentially fill the network. Occasionally you'll get a little drop when you wait for an ARQ coming back, an acknowledge coming back. Now, congestion collapse is avoided using congestion control. I recommend everybody reads this. It's not a particularly long document, it won't take you long. RFC 8085, UDP usage guidelines, before you go and start potentially flooding your network or somebody else's network. Now, I'm not suggesting you're going to take down the internet, because you're not, but you could cause yourself some challenges if you have a system which is flooding a network with data, with video data, whilst you're trying to send things like control keys, security keys, remote data, that kind of stuff. So it could be quite interesting. Right, so the problem to solve, after all of that, we've now come on the problem I'm trying to solve. And that's detect elephant flows in the fastest time possible and avoid and signal to the SDN controller to send the elephant flow on a different route to avoid mice flow latency. That's the problem to be solved. For ground to cloud, media flows are generally elephant flows, but not always. Just because it's a media flow, not a media flow, doesn't mean it's a mice flow. It could be an actual elephant flow. Somebody could, start doing a software upgrade or something without you realizing it. In IP flexible networks, why not? One solution is to manually enter the IP address into the switch to route flows. You could do that, but this is not sustainable in DHCP networks as high capacity dynamic cloud hybrid infrastructures. It's really, really difficult to maintain. I was speaking to a colleague some months ago who told me they were working on a facility that had 10,000 IP addresses. 10,000 signal flows, multicast flows within a studio. So if you think you can start manually entering flows for your ground to cloud thing, it's going to be a little bit challenging because we want to automate, as Paul and David have already said. So another solution is to use machine learning to detect elephant flows and signal the SDN controller. And this is the other part of my research. So my left leg was in IP, and now we come to my right leg, which is in machine learning. So what problem does ML solve? It allows computer algorithms to find patterns within datasets to provide classification or predictions based on unseen data. So in other words, we have to train a system. Remove the responsibility of creating a prediction or classification model away from the programmer to the data itself. So this is really important concept. This is what differs from statistics. So in statistical analysis, the data scientist has to understand the domain they're working in. But with machine learning, the data scientist building the model doesn't have to understand the domain they're working in. What they need is labeled data. And we can have lots of labeled data in broadcasting because we have lots of people who are highly qualified to do it for us. So QC, for instance, you can have QC people testing videos, and they can give you a whole list of videos which will pass or fail based on certain parameters, and that could be your labeled data. In the model I'm using here, I automatically label the data, so it can be an elephant flow or mice flow based on two parameters. And that it has to be longer than 5 seconds. The flow has to be longer than 5 seconds, and it has to be a higher average data rate of more than 5 megabits per second. So I've taken that information from papers that other researchers have used, and that's my line, if you like, is either an elephant flow or a mice flow. So I'm just going to sort of quickly, I know time is tight, so I've got to speak quickly, but I'm just going to go quickly over what ML is and isn't and how ML works at a very sort of high level. ML is not magic. It's not the answer to life's problems. I hope somebody will ask me at some point whether ML or AI is going to take over the universe and make humans obsolete, because I've got an answer. I've been thinking about it for a long time. It relies on hours or even days or weeks of training. The models I build take 6 to 12 hours to train. Some of my colleagues in the university have got models which take weeks to train. I know because we have to fight for the servers. We are heavily compute intensive for training, but much so for the evaluation and prediction and classification. So when you're doing the training, you're using oodles of processing power, but more GPU power. We'll come into the reason why we use GPUs in a minute. But when you actually do what we call the evaluation, so then you put in the unseen data through and you're using it in a real environment, the amount of process and compute power you need is significantly reduced. So as an example for the stuff I'm doing, I got 4 GPUs, RTX 5090s or something. I don't know if anybody knows about GPUs. They're super powerful GPUs with 16 gigs of memory on each one. And it'll take 6 hours to train my data set, but to do the evaluation, the actual proper application, I can run it on a Jetson, NVIDIA Jetson. So that's the comparison. So some applications, IP network optimization, we can use ML for network congestion detection, long flow TCP and ARQ detection, elephant flow and mice flow detection, and security intrusion detection as well. This is a big thing coming now in ML, and there's a lot of research going on into sort of detection of people doing things they shouldn't. You often hear of comparisons to the human brain with ML, and there's sort of good reason for it, because the brain is a biological interconnect of billions of neurons, and this is at a very simple, high superficial level. As humans learn, the interconnects are added, removed, or updated. That's how we learn. Take a baby, that's an apple, that's an apple, that's an apple. Do it enough times, and the baby goes, that's an apple. That's how we learn. The more training data the human brain has, then the better it is at predicting outcomes that the senses have not experienced before. So the really important thing is that if you teach a child to cross Oxford Circus, then they will be able to cross any road in the world, unless they go to IBC, of course. Because what we're giving them is generic instructions on how to cross a road. We don't take them to every single road in the world and say, this is how you cross this road, this is how you cross that road. Just say, here's a generic set of how you cross a road, and hopefully they learn enough to then be able to cross that road. So therefore the training is used to cross all roads. And this is what we're doing with machine learning. The more data we can throw at the system, the more sort of generalized the model can be, so the more things it can do with data it hasn't seen before, whether it's classification or prediction or whatever you've trained it to do. So this is a typical workflow of how we do machine learning. And this is supervised learning. So there are generally two types of learning, supervised and unsupervised. I predominantly work in supervised learning, which means we have to have a labeled data set. There is unsupervised learning, which I've not had much experience with, but instead of having a training set with labels, what we do with unsupervised learning is set a goal. And then you just say to the model, right, now you go and work out how to do the goal. So, annihilate the universe. Go think, that kind of thing. So with supervised learning, we have a training set with labels. So this is all my TCP data flows with the data packets that are either labeled as 1 for an elephant flow and 0 for a mice flow. We forward pass that through a neural network. I've got some diagrams of that in a sec. Compare the calculated value to the expected label value, so the output of the neural network compared to what it should be, and then update what we call the loss value, and then propagate that through the network to adjust the weights and biases within the network. So let me we'll come on to that in a sec. So ML is so powerful because the program and data analyst does not need prior knowledge of the problem they're trying to solve. That's incredibly important, because it means that as long as we've got a labeled data set, which has been labeled by experts, like the people in this room, for a specific application in broadcasting, we can give that then to a developer or data analyst who can take that data, and they just treat it as data. They don't care it's video, it's a picture. I mean, they care it's video because the different models they apply. But they just treat it as data. And then they can build models that give you the outcome, and then they can supply you with a solution. So that's where we need the data set. And through a method of learning, the model is able to find patterns to help with classification and predictions. So classification is the stuff I'm doing, EF and MF detection and classification. Predictions is things like ChatGPT, where you say, write me a thesis to finish my PhD, and it will spit something out in 10 seconds. The only problem is the chances are your supervisor got there before you. So what is a neural network? This is a pictorial representation of what we call the neuron within machine learning. So we have multiple inputs, we sum them together, we have a bit of DC offset we call bias, we have an activation function, so this takes an analog value here and sort of makes it tend towards 1 or 0 or -1 depending on what we're doing, and then we have an output. So it's like we apply data to this network and it fires a neuron. And that's why we sort of think in terms of the human brain, because that's where the similarity is. So we take multiples of those neurons and then cross-hatch them together to form a network. So each one of these is one of these, or one of these, or one of these. And the terminology we use is the input layer, which is where your raw data is coming in. Then we have the hidden layer, which is stuff going on inside. And then we have an output layer, which is giving you your response. And so when we talk about training a network, each one of these neurons has parameters associated with it. And they're sort of like multipliers and these DC offsets, weights and biases, as we call them. And by varying those weights and biases, we can generalize the model so it can respond to data it hasn't seen before and give you an output. And the way we look at that is through, or the way we train that is through a method of backwards propagation. So we pass the data through the network forward, we get our answer, compare with what it should be, find the difference, the loss value, then use that to then backwards propagate through the entire network through each of all of these, which then is used to update the weights and biases. And that's what takes the time when we're doing the learning. It's that massive calculation that's going backwards, because this is this is so simple it's useless. It doesn't do anything. The neural networks I'm playing with have got, I think, 250,000 neurons. So if you can imagine backwards propagating through those is really difficult. And the mathematics behind this is really complex and really groovy. And if you ever did A-level maths and you're thinking, what point is the chain rule? Here's the answer. If you want me to come back one day and talk about that, I'm more than happy to do so. So, what we have here is backwards propagation of gradient descent, or gradient descent, as it's also we're trying to achieve. So what we're trying to do is find these minimum loss values here. And this is where the calculus comes in, because we're differentiating the output with respect to the weights and biases so that we can then try and find our minima. If we do dx by dy equals 0, that's what we're trying to find here. Now, when we're training, and again, this is only a 3D model, the dimensions we're working with could be tens or hundreds, and it gets to the point after 3D that you can't actually pictorially represent it, so that's why we rely on linear algebra. And so, ideally we might want to be here, we might want the network to train to be here, but it gets stuck here. And so that's why we get training errors. And that's why I have to keep throwing lots of different data at it, because we want it to try and find this. But we can't see this. We just know it exists somewhere. We just know there's a solution, or we assume there's a solution. And that's why the data scientist comes in, because what they're trying to do is find the lowest value here so that they can get the best output. So these are some examples of ML models you'll hear. Recurrent neural networks used in sequence to prediction and speech data. CNNs, convolution neural networks, which are used a lot in video. If you know anybody who's doing ML in video, they'll be using CNNs and GANs, general adversarial networks, video prediction for unsupervised stuff. This is really quite sexy. Long short-term memory. This is what I'm using within my models at the moment, and these are networks which have a certain amount of memory, because one of the problems, I did start using RNNs, but one of the problems they suffer from is something called gradient descent collapse, because the values just sort of tend to 0, which makes it useless, but these LSTMs fix that. And then there's transformers, which is the next big thing, and it's the thing I'll be working on next when I get this one working properly. So, how do machines learn? That's the answer. It's all about the data, right? You must get the data set right. But the other question is, who owns the data? And this is the really difficult bit, because in academia it's great because we have all these data sets that we can use, because they're available for research. When you start building products, you have to find out who owns the data. And that can often be a very interesting question. And philosophically, that gets very deep very quickly. So what happens after learning? We've trained our network. Instead of here having, 10 neurons, we have 250,000 of them. The same model that we've trained is then used for the forward prediction. So we've done all the backwards propagation, forward learning, backwards propagation. We've now got a model which has given us some sensible answers, because we know they're sensible because we can compare the data it hasn't seen before to the answers we know it should get because they're labeled. And as long as they're close enough, we say, well, that model has learned. And the previously unseen data is presented to the model's input, so all the weights and biases are kept the same. The evaluation is performed using the forward propagation, and the results are then given on the output. So in other words, the model we've trained consists of a load of weights and biases which are used as parameters to update all our neurons. So when you've got a weights and biases file, you can then apply that to any model on any computer, which means it can just move beautifully into the cloud. assuming you can get hold of some GPUs. So when we talk about recurrent neural networks, what we're doing is effectively feeding the output back to the input. So that in the data I'm applying, I'm applying time bins. I'm taking the data of the packets, I'm segregating them into 10 millisecond time bins, and then I'm applying each of those time bins in turn to the input of the LSTM, and that's like a recurrent neural network, which is then sort of giving me the answer at the end. So in other words, it has some memory built into it. And this is the model of what I'm doing. I've got these, each one of these sequence lengths is a group of these LSTMs. It's looking at 5 milliseconds, 100 milliseconds, 150 and 200 milliseconds of data, so it can learn some of the temporal aspects of the different TCP flows, because they all have sort of different characteristics. Going into something called an MLP, a multi-layer perceptron, which is just like a summing thing that's going on there. Softmax, which gives us our 1 or 0. So this is a probability output here. And this is what I mean about the life is now probable. It's not absolute. I make it absolute because I then put it into a classifier. So if it's more than, I don't know, 50%, it's an elephant flow. It's less than 50%, it's a mice flow. So at this point, it's probable. Here it becomes certain. This is, just very quickly, it's just sort of telling you in pictorial detail what I'm actually doing. The key things here is the data set consists of 9,000 TCP points. Now, I've just increased that in the past few days. I'm using another data set called Maui, which I think is from Japan. And I've now got 55,000 data points. So my, what we call the F measure, which is part of the confusion matrix I'm using to determine the results, I was getting sort of 0.89 with these sort of 9,000 data sets. And the highest is 1. You want to get as close to 1 as you can. I'm now getting 0.92. So it's only 0.3, 0.3, but that's a massive jump in machine learning terms, because I've made it 0.03 more reliable. And this one now goes up to 11. So that's what an ML program looks like. This is the bit that's doing the work. So this is your forward prediction thing here. This is the model. We use something called PyTorch. I use something called PyTorch. There are other models available. PyTorch is one I use because my supervisor said so. Sometimes you just got to play the game, and I'm using Python. Python is sort of the de facto language for machine learning people. This then integrates into a GPU because we use, I think I mentioned GPUs in a sec. Comes to GPUs in a sec. So it is a prediction output. It gives you the label set. We then compare the labels of what it should be to what we've got. We then do our backwards propagation, and then we update our weights and biases. And that's all it does for hours and hours and hours on end. But you would not believe how long it takes to get that bit of code working. A long, long time. Right, so why are GPUs key to ML? Because in our backwards propagation, we use a form of mathematics called linear algebra, which by some interesting and strange coincidence of the universe is what GPUs use for their shading algorithms. So GPUs have been more adapted now to do more ML type work, but generally speaking, a lot of the core hardware accelerators within a GPU gives us what we need to do for machine learning. And so there we go, that's it. So as far as learning is concerned, we need thousands of data points. The more diverse the data sets, the better. The data is presented to the models, we can update our dates and biases. One of the problems we can suffer from is overfit, where we find a particular part of the data which is giving us particularly good results, and then when we put our unseen data into it next, it's rubbish, and that's really depressing. And then we sort of update the weights and biases, and we should become very concerned about data bias. Please be very, very concerned about data bias, because how are these data sets labeled? They're labeled by humans. Humans have bias. So, very quickly, I've already said this, 10,000 points of data set. That's what my data set looks like. It's just a 0 or a 1 at the beginning saying it's a elephant or mice flow. And then this is all the parameters, these are all the data rates within the actual TCP flow in 10 millisecond chunks, which gives me the data. So this is what I mean about data bias, okay? Label, adult in a jacket. Yes, it's an adult dog in a jacket. Why anybody would want to put a dog in a jacket, I don't know, but they have on this occasion. Label is classified by humans. What if the label is wrong? So in the same way you could, a parent teaching a child, if the parent is wrong, the child becomes wrong. Same with our computer systems, our ML systems. We should be really, really worried about data bias. So, putting it all together, what I've added here, so we've got our control key, security, remote control data all going into our router with our streaming video, which may be ARQ or TCP, depending on what you prefer. So ARQ is like UDP with AX, and no congestion control, unless you switch it on. I think the one I saw, you actively switch it on in the software if you can find the switch. I'm using this machine learning ensemble LSTM. That's what I've called the particular model I'm using, which is an elephant flow detection. It detects the elephant flows using the IP addresses and the TCP port numbers as a unique identifier. Sends it to the SDN controller. The SDN controller says, right, these packets coming along now, they're elephant flows, send them over this link, and they can process the other ones are mice flows, and they can go the other way. All completely automated. So nobody has to sit there programming, sort of IP addresses or anything. So, in conclusion, as an industry, we need to start thinking about asynchronous packet flows within networks that can be highly interactive, just as Paul and David were saying earlier. Just taking your existing workflows, put them into a network, is going to fail. In the same way, if we keep thinking synchronously in terms of networks, clouds, data centers, we're going to fail. We saw some fantastic examples of people now actually processing asynchronously in the cloud. One was at NAB. So it's happening, and I've always said that ST2110 was the biggest change that happened to broadcasting since Marconi EMI went head-to-head with Logie Baird in the 1936 BBC trials in Alexandra Palace, London. I now think asynchronous packet flow processing within the cloud is the next big thing to have happened to broadcasting. Seriously, seriously big. We want to keep UD media flows separate from TCP ARQ flows to avoid packet loss and congestion. Understand congestion control. Please understand what I mean by congestion control if you're building networks, you're streaming stuff into the cloud. Use SDNs to truly flex IP systems. They're the next big thing coming along for broadcasters. And ML is providing unprecedented opportunities for broadcasters, without a doubt. Data sets are the key to the successful application, but data bias is a major concern. Please understand data bias and the problems it's going to cause us as a society. And we should all question the data, as we do in life. Thank you.
Thank you so much. That was amazing. Is this working? Yeah. I think Tim is ready to run around with a microphone if anybody has got any questions for Tony.
David, please be gentle.
I'll be kind. So are you using the data rate as input to your model, or are you using the data in the packets?
I'm taking the data in the packets and I'm dividing it into 10 millisecond bins. So I'm quantizing it into, tokenizing it, into 10 millisecond bins. So if you have, say, 3 packets in the first 10 milliseconds, they get aggregated together and counting the number of bytes in the packets. And then in the next 10 milliseconds, if you only have 1 packet, then I'm counting the number of bytes in that packet, and that becomes the data value.
The bytes.
Yes,
that's the
in the
packet.
packet.
Model rather than the actual data in the packets themselves.
That's correct. Yes, it's the number of bytes is the input to the model.
I'll
yes.
give you my unkind question then.
Okay.
Why didn't you just detect that each packet started with 47 to work out that it was an elephant flow?
Because not all elephant flows.
It was a childish question.
All right. No. It's not all video flows are elephant flows. You know, you can get lots of different ones, and that's where the automation comes in.
The purpose of the model was to avoid congestion on the outbound feed to the cloud.
Mm-hmm.
Ultimately, the solution looks to me like you just smashed another network connection next to it. The model then predicts whether an elephant flow goes one way and a mice flow goes the other way. What is the theoretical performance gain of that, rather than just aggregating the two networks and saying, I've got a fatter pipe? I can send more data. I have a lower
I think
latency buffer.
I think what's that is one solution without a doubt. Just keep increasing the size of your pipe, but what you don't know is what you're connected to at the other end. So what kind of switch you're connected to? What's the buffer size? All these things work well in isolation when you have one ARQ flow, one TCP flow, one video flow, and one control flow. Say you have 50 of them going down the same pipe, because the bigger the pipe, the more flows you're going to have to put through there. And then the world starts getting random. So that's what we're trying to avoid with this, is that unpredictability. I'm trying to bring some sort of order to then sort of sort these flows out so we can classify them better and make the system more predictable. Okay.
Okay.
Excellent. Thank you.
Thank you very much, everybody. It's been a great evening, and thank you so much for all of you for coming along. I guess we should say thank you to David. Thank you to Polly. And thank you to Tony. Yay.